All right, hi everyone. I'm Konstantinos Mamouras, and I will talk about static analysis for checking the disambiguation robustness of regular expressions. And this is joint work with Alexis, Glaunec, Angela, Lee, and Agnishom, Chattopadhyay. So I guess most of us already know that regular expressions, or regexes, have several applications on text analysis. Some of the tasks that we can solve with them is checking whether a string has a certain form, or checking whether a string contains a pattern, or to find the occurrences of a pattern inside a piece of text. The first two problems are essentially the classical membership problem, but in this talk I will be focusing on the third task, which I call match extraction. For our results, we will use a very classical syntax of regular expressions, where they're built using concatenation, non-deterministic choice, and Kleene star. And I will also use a little bit of syntactic sugar for Kleene plus and the optional operator. So here is an example of a task. Let's say we want to extract substrings that have the form of a floating point number. Here is a regular expression that can be used for this task. I will explain it very briefly. So this is a character class that matches a single decimal digit. The sub-expression describes the optional sign symbol. Now this sub-expression specifies the integer part of the number. And finally, this sub-expression describes the optional fractional part of the number. So here is a piece of text from which we would like to extract the substring 28.3168. But notice that the substring 8.3 is also a match for the pattern. And so is the substring 168. In fact, there are many more substrings that are matches for the pattern, but we care for none of them. So how do we specify the desired match out of the many possible ones? One answer to this question is given by the so-called POSIX disambiguation policy that says choose the longest out of the leftmost matches. And then another answer is the greedy or PCRE disambiguation policy that again says choose a leftmost match, but then further disambiguate by using the following two rules. If we have a Kleene iteration R star, then we want to repeat R as many times as possible. And if we have a non-deterministic choice, then we prefer the left choice over the right choice. The majority of regular expression engines out there either use POSIX disambiguation or greedy disambiguation. And this raises the natural question of whether we can safely reuse patterns across these two classes of regular expression engines. This notion of safe reuse is formalized as follows. We will say that a regular expression is disambiguation robust, or just robust for brevity, if for every input string, the match that is preferred according to the POSIX policy is exactly the same as the match that is preferred according to the greedy policy. Okay, here is the pattern that I showed in the previous slides, and here is another pattern. At the top level, it's a non-deterministic choice, and the left choice specifies a number that is just an integer. The right choice specifies a number that has a fractional part. So you probably can observe that in terms of classical language theoretic semantics, both these two regular expressions recognize exactly the same set of strings. However, the first one is robust, but the second one is not. In fact, the string 3.14 witnesses this non-robustness because the POSIX policy would match the entire string, but the greedy policy would only match the prefix of the digit 3. So to see whether non-robustness is an issue in real applications of regular expressions, we have considered 4 datasets that in total contain 10,000 regular expressions. here are the main observations that we made. About 4% of the regular expressions in these datasets are non-robust. Additionally, we saw that real input strings witness this non-robustness. This means that non-robustness is not just a theoretical problem, it is indeed an issue that arises in real applications of regular expressions. As an example, let's take a look at this pattern that specifies an IP address that I took from the Snort dataset. And here is a string that I extracted from a real network traffic trace file. This string indeed witnesses non-robustness for the pattern that I'm showing. So our notion of robustness naturally gives rise to a decision problem, which I call is robust. If we're given a regular expression R as input, is our disambiguation robust? And our first theorem is a hard-order result that says that the problem is robust is PSPACE hard, which is something that we prove with a reduction from the universality problem for regular expressions. For the rest of the talk, I will try to give you a little bit of high-level intuition as to how we can actually solve the is robust problem. To obtain our results, we will use a model that I call greedy non-deterministic finite automata, or GNFAs. And this is a variant of the classical epsilon NFAs that we know. But every non-final state has one out of three types. It can either be a guarded state, which means that it has exactly one outgoing transition labeled with a character class, or it can be a jump state, which means that it has exactly one outgoing epsilon transition, or it can be a choice state that has exactly two outgoing epsilon transitions, one of which is labeled with epsilon/0, and the other one is labeled with epsilon/1. So the intuition here is that the transition that is labeled with epsilon/0 is preferred over the one that is labeled with epsilon/1. And these choice states are used to implement the greedy semantics. A key concept here is the concept of a disambiguation trace, or just trace, which is a string over zeros and ones. And a trace gives us the sequence of choices that are made in a path. Now, for the greedy semantics, the idea is that we want to choose a path that has a lexicographically least trace. And at this point, I should acknowledge that prior work has already considered such automata in the context of full regular expression parsing. To describe GNFA execution, both for the greedy and for the POSIX semantics, I will need three notions: token, priority, and configuration. For greedy execution, a greedy token is a triple Q, I, tau, where Q is a control state of the automaton, I is a start position in the string, and tau is the disambiguation trace of the corresponding execution path. The greedy configuration now is a linearly ordered list of the greedy tokens. For the POSIX execution, on the other hand, a POSIX token is a pair Q, I. A priority is simply a start position I. And a POSIX configuration is a partially ordered list of POSIX tokens. Both for greedy and for POSIX execution, at every step of the computation, we consume a letter and we update the configuration. And here's where priorities come into play. At every step, we process the tokens of a configuration in order of priority. So given all these things that I just mentioned, how can we actually check the robustness of a regular expression? So here's a first thought. Let's consider the greedy and POSIX executions over every possible input string, and we should check that there is always agreement in output. but of course this involves an infinity of checks. We have to work a little bit harder to obtain an actual algorithm. Our first observation is that when we scan a string from left to right, disagreement between greedy and POSIX can only occur by having a new, better POSIX match, while the greedy execution does not report a new match. And the second crucial observation is that we do not even need to record the greedy and POSIX priorities in order to identify non-robustness. This means that we can drop all this information that has to do with start positions and disambiguation traces. So this gives rise to the concept of a stripped greedy execution, where a configuration is an element of list of Q, which means that it is a collection of linearly ordered control states. And correspondingly, we have the stripped POSIX execution, where a configuration is an element of list of set of Q. So we think of it as a collection of partially ordered control states. Now, the robustness analysis checks that the stripped greedy and POSIX executions are always in lockstep. This means that they always agree in terms of finding new best matches. This analysis can be formulated as the exploration of a finite graph that I call the robustness graph. It consists of vertices that are triples, where the first component is a stripped greedy configuration, the second component is a stripped POSIX configuration, and the third component is a Boolean value that indicates whether a match has been found so far or not. So let me use the example of the GNFA for the regular pattern A star AB option in order to illustrate the exploration of the robustness graph. And in particular, I will be using breadth first search because I would like to find a witness of non-robustness that is of minimal length, if one exists. So in the beginning, we construct the initial vertex. And notice here the annotation on the edge. This annotation says that greedy and POSIX agree because both of them report on a match at the very beginning. This is because the regular pattern accepts the empty string. Then we continue our exploration by considering the edge on the letter A from the initial vertex. This gives us vertex 1 of the graph. Again, we see that greedy and POSIX are in agreement because both of them report a new best match. Then we will explore the edge on the letter B from the initial vertex. Again, greedy and POSIX agree because both of them do not report a new match. And also notice that in vertex 2, both configurations become empty. Now we will continue our exploration from vertex 1. If we consider the edge on the letter A, then we form a self-loop on the vertex. We see that greedy and POSIX again agree. Both of them report a new best match. And then let's consider the edge on the letter B from vertex 1. And here finally we notice that greedy does not report a new best match, but POSIX does, which means that we have just identified non-robustness, and we can read off the witness of non-robustness by following the path from the beginning until this point where we witness the non-robustness. And in our case, it's the string AB. By the way, here the analysis would stop, but this is not the complete robustness graph. Here is the part that is missing. Okay, using all these ideas that I just described, we can now finally prove that the problem is robust, is PSPACE-complete. I have already discussed that the problem is PSPACE hard. It remains to see that the problem belongs in the class PSPACE. So the first observation is that the robustness graph has exponential size, but we can construct it on the fly. And we can explore it using a non-deterministic polynomial space algorithm that intuitively, at every step, guesses and checks the witness of non-robustness letter by letter. Then finally, we invoke Savage's theorem, and we obtain the desired result. We have implemented the robustness analysis algorithm that I just described, and I call this the base algorithm. We have also implemented some performance optimizations that rely on some easier to check sufficient conditions for robustness before we run the base algorithm. I'm not going to be able to give you the details of that. More information about these optimizations can be found in the paper. In these plots, you can see the comparison between base and opt. The horizontal axis shows the running time of the base algorithm in milliseconds, and the vertical axis shows the running time of the optimized algorithm. Every point in these plots corresponds to a regular expression, and the observation is that all points, or rather most of the points, are substantially well below the diagonal, which means that the optimized algorithm is faster than the base algorithm. Here's a table that summarizes the results. The base algorithm needs a little bit over an hour to analyze all the regular expressions in our datasets, and the optimized algorithm needs roughly 2.5 minutes to do so. Another thing that I should mention here is that the base algorithm fails to analyze roughly 3% of the regular expressions because the space blows up. But the optimized algorithm fails to analyze less than 0.04 of the regular expressions. I'd like to conclude with a summary of the main points of my talk. First of all, we have defined the novel notion of disambiguation robustness for regular expressions, and we have seen that non-robustness is an issue for reuse in practice. We have shown that the problem of deciding robustness is PSPACE-complete, and we have proposed an algorithm for robustness analysis that relies on the exploration of an exponentially large robustness graph. Finally, we have implemented our robustness analysis algorithm, and we have shown that it can analyze the vast majority of regular expressions in the data sets that we have considered in a few milliseconds per regex. This concludes my talk. Thank you for your attention.
Fitz. Thank you very much. Wonderful conclusion to the conference. But I've worked on some of those things myself, so I was wondering, it seems like you have developed a sort of monotonic way of representing the states of, for a streaming exploration of an input, you could say, by representing the not only the greedy state, which looks very recognizable to me, but also the longest prefix one. So, is that a basis then for having a sort of single pass streaming longest POSIX style algorithm that can do full parsing or of regular expressions? Here you're actually studying the relation of those two.
Right. That's a great question. So actually the semantics that we consider will only look at the match for the entire regular expression. So we will not further parse the substring in order to go into the realm of full parsing. We will just identify from where until where the overall match is. So I would say in that case, it would be a lot easier to get a streaming algorithm. But in the case of full POSIX parsing, I don't think it would be such a simple step to go from what we have developed in the paper to an algorithm that can give you the full parse tree for POSIX semantics. I think that might require some additional algorithmic tricks.
I'd like to chat with you after that.
Yeah.
Okay, I have one question. So I wonder if there are some connections between this robustness problem and grammar ambiguity. So there are some techniques that analyze ambiguity of arbitrary context-free grammars. So have you thought of that connection?
Right, so it's a different notion. So the notion of ambiguity also exists for regular expressions as well, but it's an easy problem. Like to check ambiguity for regular expressions is just a simple reusability algorithm over a small automaton. So this notion is fundamentally different. Like,
Right, but I wonder if you could encode this robustness problem as a grammar ambiguity problem, or maybe that doesn't make sense.
I don't see the encoding right now, but maybe there is a connection. Yeah.
Hey, I was wondering, so these tools, they don't just differ in how they match the longest string, oftentimes they differ in the actual regular expression language. So like they have more things than these things, for example, matching things after like a kind of look ahead sort of things. Have you looked at, could this be adapted to support kind of more kind of in the wild regular expressions?
That's a great question. So before I get to look aheads, I want to say something about another feature that takes us beyond classical regular expression back references. Our results actually also show that deciding robustness for regexes with back references is undecidable. So we can forget about regular expressions with back references. Now for look around, I believe that this can be accommodated. I don't think that the essence of that extension would be fundamentally different than what I showed. I feel like it would become a little bit more hairy to describe, but I think fundamentally the same idea as what I showed today should work for pure look around. So both look behind and look ahead, actually.
Okay, so that concludes the session and the conference. So thanks again for all the great talks and great questions.